Sometimes a molecule might have an overall charge. We haven't really talked about these too much. We just kind of skipped over this section in chapter 7. We want to talk about it now, though, because now we know what a molecule is. We know how to draw them. So if I have like a PO4 is a grouping of nonmetals. So the phosphorus and the 4 oxygens are probably sharing electrons to make all their noble gas configurations. And if I put all the valence electrons I have in there, given that I have 3 extra electrons to make it a 3 minus charge, that is going to complete the noble gas configuration. And when I look at all the formal charges, I realize that I've got 3 extra negatives. So as a group, that has an overall negative 3 charge. And since it is an ion, it's also a molecule, because it's a group of atoms sharing electrons. So if it has an overall charge, it can attract other ions. Right? So if I have an ionic compound that contains a polyatomic ion, which is just a molecule that has an overall charge, if I'm going to combine ions together, I still have to make sure that the formula has a balanced overall charge, which we talked about already. Right? We said, if I'm going to make a solid from this, an ionic solid, and I'm going to take this piece that's a negative and this piece that's a positive and allow them to attract together, I have to create a unit that repeats over and over again in that solid. And the overall unit that's repeating has to be neutral. Because if I just took one of each of these and I had an extra negative, because there's a 3 negative and a 2 positive, that extra negative repeating over and over again would cause a huge amount of instability due to all that extra imbalance in charge. So my individual unit in an ionic compound has to be balanced. So that means the formula has to account for that. So I take the charge on one compound, make it the subscript for the other substance. Take the charge here, make it the subscript for that substance. That gives me 2 of these negatively 3 charged items, because the subscript for that is a 2, so that's a total of negative 6. And I've got 3 of the Ca2 pluses, that gives me a plus 6. So now the formula gives me a balance in charge. There are lots of molecules that have an overall charge. So obviously you don't have to memorize these, you don't have to memorize them, it's just pointing these out. Lots of situations where 2 atoms will share electrons, or more than 2, but when these atoms come together to share their electrons to make their noble gas configuration, there may be an overall net extra electron just to get both atoms to be able to make their noble gas configuration. And so sometimes you end up with this extra charge existing on a certain atom as a formal charge. That creates an anion or a cation, which can then attract other anions and cations to make ionic compounds. So we talk about ionic compounds, we talk about covalent compounds. Sometimes a compound is both. Right? And that was the example here. The Ca3PO42, this is both ionic and covalent. There's an ionic attraction between the calcium and the PO4, and there's a covalent attraction directly between the phosphorus and the oxygen. So if the covalent attractions create a structure with an overall negative or positive, it can still attract other ions of the opposite charge and form ionic compounds. Now there's one other type of compound that's mentioned in Chapter 5 that we want to sneak in here, and that is called a hydrate. A hydrate is a compound that usually involves an ionic substance forming some real strong ion dipole attractions with water. So what this looks like is you've got these ions like a copper sulfate. So the copper has like a 2 plus, and the sulfate as a unit has a 2 minus, and those are balanced in charge. So in this case, the ratio is, oh, that's a mistake. It's a mistake here. This 4 should be inside here. The ratio of copper 2 plus and SO4 2 minus is 1 to 1 because they have the same charge. So if I made a compound of that, there's a couple different forms it could take. I could make it anhydrous. Sometimes you hear the word anhydrous. That means no water. Anhydrous is like dehydrated. Dehydrated. There's no water. So if I had anhydrous copper sulfate, I wouldn't have this. I would just have one copper and one sulfate. The SO4 2 minus and the copper 2 plus would be repeating over and over again in order to make a ionic compound with lots of ionic attractions between the opposite charges in an organized way. But sometimes these types of salts or ionic compounds will form hydrates. So instead of making an organized solid by lining these up and only these, there may be some number of water molecules that surround these charges through ion dipole attraction. And each repeating unit, instead of just being the ions, each repeating unit will include some waters surrounding those ions, and then that, with the waters intact, will become the repeating unit. And that's called a hydrate. And those are pretty common because water is all over in our environment. It will just naturally come in from the atmosphere, and moisture in the air will come in and start to surround these ionic compounds. Yes, they're formed, well, technically, they're formed through ion dipole attraction. Because the water has a large partial charge and the ion has a full charge, so a full charge attracted to a partial charge is technically an ion dipole attraction. It's stronger, it's even stronger than a hydrogen bond. So the water molecules get in there. I mean, water molecules can attract other water molecules through hydrogen bonds. Partial positive, partial negative, that's a hydrogen bond. That's a pretty strong attraction. But the water molecules can form even stronger attractions if they come in here and surround these ions. So it's a natural tendency for moisture from the air to come in and get in onto the surface, or even sometimes when this, if this ions form a solid by coming together in water, water can get embedded in there because of the ion dipole attraction between those two being strong and pulling them together. So if each repeating unit, if this copper sulfate combination, if each repeating unit of that happened to be surrounded by 5 waters, that would be the formula showing, and this dot is showing the ion dipole attraction, showing that the waters are not really covalently or ionically bonded to the copper and the sulfate. They're surrounding it, forming an ion dipole attraction. So there are lots of different varieties of hydrates with different quantities of water. I can make this salt get surrounded by 4 water molecules. I can make the barium chloride get surrounded by 2. So the number of water molecules is usually part of the chemical formula. It tells me, the chemical formula tells me if I took a repeating unit of this, what's actually in that repeating unit. If there's waters involved in that repeating unit, I have to tell how many, and that goes into the formula for my hydrate. So if you take that hydrate and you heat it up, since the waters are only involved through a ion dipole attraction, which has some strength, but if I heat it up and give it more and more temperature, more and more motion, eventually the water is going to be moving enough where it's going to break this attraction, it's going to evaporate out. So I can convert a hydrate into an anhydrous ionic compound by heating it and causing all the water to evaporate out. And that evaporation off of the water gives me an anhydrous salt or ionic compound if I want it to be anhydrous. And then often there's a difference in appearance. So here's the so this is the anhydrous version, and then the hydrated version I think has the water molecules associated with it. Or maybe I'm getting those backwards. I'm not totally sure which is which. Oh, there's the answer. I was wrong. The difference in color has to do with when the light from the light bulb, the white light hits that sample, and the white light hits it. If some of those wavelengths get absorbed and others bounce off, in this case you would see the blue light bouncing off, that bounces into your eyes and you see that. So the white colored powder there isn't absorbing any light in the colored region, so all the white light comes off and bounces to your eyes and you still see it as white. That's not really the most important part here. Just want to do one other quick example here, just to illustrate. If I give you a couple formulas to deal with, so if I tell you that you have an ionic compound and I want you to give the formula. I might do something like this. I might say you've got magnesium combined with, since we're not memorizing the names of the polyatomic ions, I would have to give you a polyatomic ion. So I might say bicarbonate, which is an HCO3 minus. Right? So that's a molecule that happens to have an overall -1 charge. So I want you to combine that with magnesium, and I want you to make like a trihydrate. So what would the formula be for that? Because tri means 3, and the hydrate means waters. So that would be a magnesium. And what should the charge on the magnesium be? A +2. Because it's in group 2A, it needs to lose 2 electrons to make the same number as a noble gas. So it'll have 10 electrons, and that will give it a +2 charge. And I'm already showing you the charge on the HCO3. So if that unit only has a negative, how do I fix the formula? Right, I have to put that whole thing in parentheses and say I've got 2 of those so that the charge is balanced. Then if I have a trihydrate, I would say that there are also 3 waters associated with each repeating unit. And that would be the formula, because that represents the unit that's repeating over and over again if I have a sample of that. It'd be magnesium bicarbonate trihydrate, but the name is not really as important as recognizing. So the skills here that you have to be able to do are, if I give you an individual element, you need to know the charge based on how it makes a noble gas configuration. If I give you 2 substances that are both charged, you need to recognize that the ratios must create a charge balance. And then if there's some waters, you need to be able to understand how to write that with the dot there, instead of including the waters in the formula some other way.